Thank you very much, fellow Kenyans. I'm Honorable Babu Owino, Member of Parliament in Embakasi East constituency, and also a teacher who's been leading some our students through their tutorials, the revision on KCSE examination. Today we have a special guest who is Mr. Gishui. Mr. Gishui is a chemistry teacher and also a mathematics teacher. He has been recommended to us by some of his former students and also the current students. Also his colleagues recommended him to us that he'll be handling. We decided to invite him to handle chemistry lesson today on a topic called mole concept. I hope you will enjoy. Stay tuned. And after this lesson, I'll proceed with the lessons on a weekly basis. So kindly just stay tuned. Today we want to give an opportunity. Today we want to give an opportunity to one of the teachers in the nation, and in the coming days, in the coming weeks, we'll also be introducing some of the teachers, at least to give them an opportunity to help our students pass the examinations. Hope you'll enjoy. Welcome, Mr. Gishui. Karibu sana.
Thank you.
Okay. Sawa.
Thank you very much, Mheshimiwa, for this opportunity that you've given me to serve Kenyans in this new capacity as a teacher online. This is something I'm not used to, but I believe that I'll be dealing with the over 40 students that I've always handled before. First and foremost, I want to say that I'm very, very grateful to Honorable Babu for the good work he has continued to do to his constituency, and also to reach the Kenyans in this way. In the words of Professor Wangari Maathai, who said that do something, but don't just sit. Just like that little hummingbird that was trying to stop the fire that was raging a forest. Mwalimu Babu has tried to do that, and this is where I'm joining in to deal with chemistry, as you can see. And the topic today is the moles. Today the topic is the mole, and I'm saying that the mole is simply a unit of measurement, just like the way we would measure distance, and the SI units for distance are the meters, symbol M. The mass and the SI units are for the grams, and simply symbol G. In our day-to-day lives, we also talk about a pair, meaning 2 units or 2 pieces, a pair of trousers, a pair of shorts, a dozen of eggs, 12 units, a dozen of pencils, 12 units, a crate of soda, a crate of liquor, 24 pieces. And therefore, when you're dealing with a mole, it is simply a unit of measurement. It is the SI unit of measurement in chemistry. And what a mole is simply defined as the amount of substance that contains equal number of particles as there are in 12 grams of carbon-12. And here we are saying which are the particles that we are talking about in this case. We are dealing with the atoms, the molecules, the ions, electrons, and so on and so forth. Now, which is this number of particles we are talking about? In the case of a dozen, 12. In the case of a mole, we are dealing with 6.023 times 10 to the power 23. Now, how did we end up to this number? This number, the 6.023 times 10 to the power 23 particles, was after several experiments by an Italian physicist who was called Amedeo Avogadro. And this man lived between the 1776 to around 1856. That's around 80 years. He was blessed with that number of years for doing the kind of work the young MP Babu is doing to our country. So in this case, you find now this number is too large. This number is too large. 6023 to power 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. This number is too large to talk about, and this number is the one that we found every 1 mole that contains this number of particles was given as by the Avogadro, and this is the 6.023 times 10 to power 23 particles equivalent to 1 mole. So when we are dealing with 1 mole, we are dealing with an atom, like say atoms. This is sodium with a relative atomic mass of 23. So in this case, you find if we take 23, this has no units. It's a relative unit. So there is no units for this. And therefore, if we take now the 23 and we take them in grams, 23 grams. So the 23 grams would contain 1 mole, which is 6.023 times 10 to power 23. Now particles, which are the particles here talking about? Relative atomic mass. So these are the atoms. Once again, we are saying the relative atomic mass, as we found out in Form 2, that this lamb is the mass of an average atom, the mass of an average atom compared to 1/12 mass of 1 atom of carbon 12. So because we are simply relating, it's not absolute measurement, then these units have no, these masses have no units. Relative atomic mass have no units. So we are saying another atom, the RAM, taking it in grams, and then the moles. We can take the first one here, as we have noted. We can take aluminium. This is 27, and therefore 27 grams of aluminium will be equivalent to 1 mole. Why 1 mole? Because the 27 grams, if we use a mass spectrometer and other machines, we will find it contains 6.023 times 10 to power 23 atoms. Now in this case, for purposes of simplicity, we can simply call it 6 times 0.0 times 10 to power 23 atoms. So this is approximately that for purposes of working out easily for this lesson. If therefore we are dealing with now 2.7 grams, 2.7 grams, 2.7 grams of aluminium will be how many moles? Here we would say 2.7 cross multiplication times 1 over 27, giving us 0.1 moles. In other words, we can convert from the masses, the grams, into moles. And also we can convert 1 mole. We have discovered a 6.0 times 10 to power 23 atoms. What about 0.1 moles? Cross multiplication gives us 6.0 times 10 to power 23 times 0.1, all this over 1. This gives us 6.0 times 10 to power 22 atoms of aluminium. We can also note that we can convert from moles to moles to number of particles, or from moles to the mass. You have noted by formula that the moles equals the mass given. The mass given, all this divided by the relative atomic mass, the RAM, but now in grams. The moment we take that, then we can get moles, and then the number of particles would be given by the moles times the 6.0 times 10 to power 23 particles. Now, what name is given to this number of particles? The Avogadro. We refer to it as Avogadro's number. Simply, you can write it as the Avogadro's number as symbol L. Avogadro's constant, whichever you use, constant, capital letter A, N, and capital letter A, written like that, the Avogadro number, and that is the 6.023 times 10 to power 23 particles. And we have said, for purposes of this our lesson, we can simplify this or approximate this to 6.0 times 10 to power 23 particles. Now, from there, we can still look at another set, and this one we are looking at molecules. Molecules include, we have looked at atoms. Now we want to look at the molecules. Molecules include things like oxygen. It's a molecule, it's a covalent compound. Hydrogen gas, ammonia gas, water vapor, hydrogen chloride, all these, methane gas, sulfur 4 oxide, sulfur 6 oxide, etc, etc, etc. Now, when we want to look at this molecule, the mass of all these can be worked out. How do we work out the mass of oxygen? We know in our periodic table, the atomic mass of oxygen is 16, written as a superscript, and we have 8 as the atomic number. Now that oxygen is diatomic, 2 atoms combined, means that the mass is the sum of the individual atoms. So oxygen is 16 plus 16, that is 32. That makes it the relative molecular mass. So when we take, now in this case we take the molecule, After we take the molecule, we then take the mass. And we are saying that this is the relative molecular mass, the RMM. When we convert that relative molecular mass into mass in grams, then that number, we get the number of moles. So for instance, here we can take hydrogen chloride. The mass for hydrogen is 1 plus 35.5. This gives us 36.5. Because we are dealing with the relative masses, there are no units. But now when we take the mass now of HCl and we weigh 36.5 grams, the number of particles in here are 6.0 times 10 to the power 23. Now, because we are dealing with molecules, then these are molecules. And these molecules are the ones we are saying, because of this number, then that is 1 mole. So in our case, we are therefore saying 36.5 grams of HCl is equivalent to 1 mole. And also, the number of HCl particles, which happens to be molecules, are the Avogadro's constant. So if we take now a simpler mass, or even a bigger mass, like say 365 grams of HCl, we are saying this is equivalent to how many moles? So that 6.5 is 1 mole. What about this? We simply cross multiply times 365 divided by 36.5. This gives us 10 moles. We are dealing with 10 moles. And the 10 moles in this case can be converted into the number of molecules. So 1 mole is equivalent to 6.0 times 10 to the power 23 molecules. What about 10? Here, class, remember, you cross multiply again. 6.0 times 10 to the power 23 divided by 1 times 10. So this gives us 6.0 times 10 to the power 24. What are we dealing with? Molecules. Similarly, we can take another one, say methane. Methane, carbon from the tables has a mass of 12, so that is 12, plus 4 hydrogens, each has a mass of 1, so that is 16. Relative molecular masses, no units. But when we now take 16 grams, then that gives us 1 mole. And that 1 mole, we are saying, is 1 mole of methane gas molecules. So, which is equivalent to 6.0 times 10 to the power 23 molecules of methane. So, if you wanted to do any conversions, 0.016 grams. How many moles are these? 16 grams is 1 mole. What about this? Simply cross multiplication. Simply take 0.016 times 1 divided by 16. This gives us 0.001 moles. So it is very, very simple when we take the mole as a unit of conversion, a unit of measurement. But if we take the mole otherwise, then it will be very, very difficult. Now we can look at other compounds that exist, and we can take a compound, say sodium oxide. This compound, you discover, has sodium, 2 pieces of sodium and 1 atom of oxygen. So if you want to get the mass, it is 23 times 2, which is there 2, plus 16, giving us 46, plus 16, and that is 62. So that is, now these are relative masses. So this mass is relative formula mass, because this compound is not a molecule. So we can't call it molecular mass. This compound has two different elements, and a metal and a non-metal, which is ionic. And for ionic, then we talk of relative formula mass. So when we take now the mass in grams as a unit of measurement, then we are going to take 62 grams of this compound. If we measure, will give us 6.0 times 10 to the power 23 particles of this, which is therefore 1 mole. So we are working out the relative masses, converting them to the grams. So the relative formula mass is the same as the mass, but in grams. So if we have 6.2 grams of sodium oxide, then this gives us cross multiplication, this 6.2 times 1 divided by 62, this giving us 0.1 moles. And we can convert which are the particles in it. These are the ionic, it's an ionic compound, so we are dealing with these particles combined will be 6.0 times 10 per 23 for every 1 mole of that compound. Now, in that case, we can take another one for your example, and this one is maybe potassium chloride. The mass of potassium will be 39. That of chlorine is 35.5. If we sum that up, we'll get 35. This is 5. This is 4. Carry 1. So 74.5. No units. But when we weigh 74.5 of this compound, then we are saying that is equivalent to 1 mole. So whatever if you are given, for whatever reason, the examiner chooses to give you 0.745 grams to be converted into moles, then you simply cross multiply 0.745 times 1 divided by 74.5, and here you simply get 0.01 moles. Similarly, if you take another example for purposes of your working, sodium chloride. Sodium has a mass of 23 from our tables, and these masses are provided. You don't have to go cramming all that. Then you add it to the mass of chlorine here, you get 35.5. So when you add the 2, you get 5.8, and this is 58. So when you take 58 now, if you weigh sodium, you weigh 58.5 grams, then this is equivalent to 1 mole. As simple as that. So if you take 585 grams, cross multiplication, here you take 585 times 1 divided by 58.5, you get 0.1 moles of sodium chloride. Taking another example from the same vein, we have sulfuric 6 acid. Now hydrogens here, this is the compound, this is the relative formula mass, and then we will convert it into mass in grams. Then we will be working out the moles. So in this case, you get hydrogen 2, sulfur has a mass of that 2, here, and it's only 1, then plus 16 times 4 is 64. This gives us 98. So if you take now, has no units here. So if you take 98 grams now of this, then you're saying this is equivalent to 1 mole. And therefore, if you're given 0.49 grams of sulfuric acid, then the examiner asks you to get the moles. It is simple. You simply take 0.49 times 1 divided by 98, and here you will get the answer. You can simply feed these figures in your calculator. You can work out several in this line, and I'll give you, you feed, get sodium carbonate, get the relative formula mass, work out that, then give us the moles. Step number 1, you fill in the blank spaces. Step number 2, I come here and give you 0.106 grams of sodium carbonate. Fill in that. In other words, you are getting the moles. Here you get the moles. Then that is number 1. Number 2, number 3. We can give you a salt that is hydrated. A salt like sodium sulfate with 7 molecules of water of crystallization. And this is what we are saying, sodium sulfate hepta. Hepta for 7. Heptahydrate. So this is sodium sulfate heptahydrate, meaning the number of water molecules present here are 7. Now we can work out the mass of this. The mass here will be sodium 46. You add to sulfur, which is 23. That gives you 9, 6. Then oxygen here. Sorry. Here we are saying the mass here is 46 for sodium. Sulfur is that 2. That is 878. Then oxygen is 16. 16 and there are 4. So this is 214. Then we have 7 water molecules. 7 water molecules. Now water is written like that. This is 2 for hydrogen plus 16. That gives us 18. Now 18 we are multiplying by 7 to have the 7 water molecules. So this is, now the total will be the total here will be we have 142 plus this is 656 12 plus 126, that is 862. So in this case we are saying sodium sulfate heptahydrate has a mass we check what we have just got, 268. So the relative formula mass is 268. So in other words, we are saying this is the compound and this is the mass. So when we take the mass in grams, then it is 268 grams. So this is equivalent to 1 mole. And therefore, if you want to convert, then we are saying if you have 2.68 grams, then how many moles are these? 2.68 times 1 over 268, which is approximately 0.01 moles. And you can continue working out like that, and so on and so forth. Let us see whether we have been working out correctly. So we are dealing with the compounds, their relative formula masses, and then converting these masses into grams. So 62 grams for this. This is 74. That is 58.8 grams. So, and this is 1 mole. This is 1 mole. This is 1 mole. So the examiner gave us this. So in that conversion, 6.2 times that, then we get 0.1. 74.5 grams is 1 mole. What is 0.745 grams? Cross multiplication. This is 58.5 is 1 mole. Then this is 585. So this is 585. So here we made a mistake, and therefore this is 10 moles. 10 moles of sodium. Then we came to this one, similar mathematics, and then you work it out. You can continue working out like that, and for this one I can give you an assignment. This is the relative formula mass. So number A, what is 134 grams? How many moles? 0.134. How many moles? You work it out. That is B. And then C, this is 0.00134. Simple mathematics, and work out the moles for your assignment. Now from there, how can we derive this formula? We can deriving or determining, to determine the formula. How do we determine the formula? Now we could have a very simple example here, burning. You can take a simple example, burning of magnesium. And these are magnesium ribbon or magnesium shavings, sorry. And what do we get? So we take a crucible, then pipe crate triangle, then we put magnesium in here. This is magnesium. If we weigh the mass of magnesium in grams before heating, this is before, then we weigh the product. When we burn magnesium in excess of oxygen, then we'll get a product which is the oxide of magnesium. So if we weigh the mass before and then we weigh the mass after, then it is possible for us to determine, it is possible for us to determine the mass of oxygen used. For instance, if we started with 2.4 grams of magnesium, and then when we burn it in oxygen, the product will be heavier than this. Reason being, we will have added oxygen. So if the oxygen added, and then the mass comes to 4, here we can have 4.0 grams. These are hypothetical values, but let us see. So the mass of oxygen used must be the final mass, 0.0 minus 2.4. This gives us 1.6. Such that now, if we have the elements, we have the magnesium and we have the oxygen. Now, what is the mass that we were given? So these are the compositions, the mass. We started with 2.4, and the oxygen that we used, excess oxygen, but the only one that was used was 1.6. So we can now work out with the lamb. This is 24 and this is 16. Where am I getting this? This will be provided for by the examiner when we'll be working them out, and therefore we can get the moles. The moles here is 2.4. We divide it by 24 to give us 0.1. Then this is 1.6. Dividing it by 16, we'll get 0.1. So we cannot stop at that. Then we simplify. How do we simplify? By dividing by the smallest. 0.1, 0.1 giving us 1, and 0.1 divided by 0.1 giving us 1. And therefore the ratios here will be 1:1. And the formula therefore will be magnesium is only 1 and the oxygen is 1. So in that case we can work out the mass. The mass for magnesium is 24 plus the mass for oxygen is 16. So this gives us 40. So if we take, this has no units, they are relative masses. So if we take now 40 grams of magnesium oxide, that gives us 1 mole. And we can do any conversions that we wish. So that process of what we've just done, we have looked at how we can get the formula. This is referred to as the empirical formula. And we have seen how we can derive it, how we can determine. We can still take another example, and this example is when we take a setup like this. We take hydrogen, and for that matter dry hydrogen gas, we bubble it or we pass it over heated this is a setup that we are using to determine the formula of a compound. This formula, so here we have what we are calling copper 2 oxide. We want to know how we can determine this formula, and this is dry hydrogen. Now when we heat this mixture, you heat, and before you heat, you pass hydrogen in that setup. Why pass? You pass hydrogen to drive out any air in the setup, to remove it. So you pass dry hydrogen, and then here you will have, not dry hydrogen, you drive out any air in the setup. Then here we are saying you heat, then you combine with hydrogen. The copper, this is hydrogen, from our form 2 work, plus copper 2 oxide, we would get copper plus water. Copper plus water. So in this case, you take hydrogen, this one is black, and this one is brown. So how do you establish that the reaction is complete? You establish that the reaction is complete when the black copper oxide changes to brown. Then you will have noted that all the copper oxide has been reduced. So initially, therefore, if we weigh the mass before, if you weigh the mass of the oxide before, and then you weigh the mass after the reaction, then you would get the mass of the oxide, and then after you will get the mass of copper. Now, in this case, you establish that through an experiment, and an experiment here done for us, we would get the mass of copper here is 2.8, and the mass of the oxygen used, the mass of copper oxide before was 3.5, and these were in grams. These are in grams. So the mass of oxygen, how would we get it? The mass of oxide minus the mass of copper, that is 3.5 minus 2.8, simply 0.7. So from there we can work out the formula. We have the elements. This is copper and this is oxygen. Now in this case, what we are noting is that the mass that we've been given, this is 2.8 and this is 0.7. So we have the RAM. This is 63.5 from our periodic table. 0.7, this is 16 as the RAM. So you work out the moles. 2.8 divided by 63.5 and 0.7 divided by 16. Work it out, just 2 seconds. You see whether you will get the same answer as I'll get. This one now, I can see that one 0.0441, and the other one 0.0438. So we simplify. How do we simplify? Divide by the smallest. and this one gives us 0.0441. This one is bigger than this, so use 0.0438, and 0.0438 divided by 0.0438, this one gives us approximately 1, and that one, so the ratios here, you get 1:1, meaning the formula, this is copper oxide. Now this formula that we've just worked out, we are calling them empirical formula. In short, EF. That is the empirical. And how do we define empirical formula? This is the formula showing the simplest ratios in which compounds atoms combine. Now, in this case, you can still work out others in a similar manner, and you can determine them like that. And from there, we can work out other things. When you have been given copper sulfate, or when you've been given magnesium sulfate, or when you've been given sodium carbonate, when you've been given all these compounds, in that these are their empirical formula. Let's take an example of sodium carbonate. In this case, we are saying that sodium has a mass of 23, and there are 2, so you will get 46. Carbon has a mass of 12, and it's only 1, so the mass is 12. Oxygen has a mass of 16, and there are 3, you'll get a mass of 48. So when you add all this, you get 106. So if you can still work it out and see the percentages. What is the percentage by mass of sodium? So percentage composition. So in this case, we are dealing of sodium. This is 46 divided by 106 times 100. That one will give you the percentage composition. Then you can work out percentage of carbon. In that compound, you would get 12 divided by 106 times 100. This one you would get the percentage of carbon. Then you come to percentage of oxygen. You would get 48 divided by 106 times 100. Then you would get the percentage compositions. If you're given these percentage compositions, you can still work back. You can still work back and get the empirical formula. Let us take an example. Let us take an example of a compound of silicon. A compound of silicon containing silicon compound containing, and we see what happens. In this case, it contains 47% silicon and the rest is oxygen. So what that one means is that the elements that you have silicon and you have oxygen. Here we've not been given the masses, but we can still work out with this. So percentage composition. In this case, the composition for silicon we've been given is 47. And because there are only 2, so we take the total percentages is 100. So 100 minus 47, then you'd get something like, say, 53. So you still repeat what we are doing. RAM, this is 28 and this is 16. So you work out the moles. This is 47 divided by 28 and this is 53 divided by 16. Here work it out and then compare with what I'll give. This is 1.68 and this other one is 3.31. You check with mine whether that is what you are getting. Now to simplify, you will take this and that, and to simplify you take the smallest and use it to divide the others. 3.31, 1.68 we divide by 1.68. 3.31 we divide by 1.68. This is approximately actually 1 and this is approximately 2. In that, so the ratios now, the ratios will give you 1:2. So the empirical formula will be silicon is 1 and oxygen is 2. That becomes the answer to that. Now if you want to work out the mass of this, the mass from our tables will get silicon is 28 plus oxygen, here oxygen, and there are 2 is 32. This gives you 60. So in other words, the relative formula mass, this yes, molecular mass of this compound is 60. So if we take 60 grams, then of silicon oxide would be 1 mole. And the rest of the chemistry follows what we did. This is the empirical formula. The formula showing the ratios in which the elements combine. Now we can consider another thing, something we call hydrogen peroxide. Hydrogen peroxide, if written like that, if we simplify this ratio, we will get like that, and therefore this becomes the empirical formula. Now what does this one become? This is the formula of this compound as it exists, showing the exact formula. We can take another one, say sodium peroxide, written like that. If we simplified these ratios, we would get that 1:1, meaning this is the empirical formula. So what does this one become? Then we still take another example, and we can take another one called benzene. Benzene is C6H6. If we simplify this ratio, we will get that 1:1. So this is the empirical formula. So this formula is giving us the exact ratios the exact numbers of the way benzene is written. Glucose C6H12O6. If we simplify, dividing everyone by 6, H2O. So this becomes the empirical formula. So this becomes now, in this case, the molecular formula. And you can see that the empirical formula multiplied by a certain integer would give us molecular formula. In other words, molecular formula is a multiple of empirical formula, where n must be an integer. This is a whole number. Cannot be n, cannot be a fraction. And we are saying if you multiply empirical formula by n, you get molecular formula. In other words, the two are related. And when we get the mass of that compound, of this compound, then we get empirical mass. So similarly, if we multiply the empirical mass by n, then we would get the molecular mass. So in other words, here we are saying empirical formula times n would give us molecular formula. And similarly, molecular mass, empirical mass times n would give us molecular mass. That one we can work out an example here, and we see what would happen if we take that example. A hydrocarbon consists of carbon and hydrogen. So when you give a sample was found to contain 92.3% carbon, and the rest is hydrogen. Now, given that the molecular formula, given the molecular mass is 78. Work out both the empirical formula and the molecular formula. Simple stuff. Carbon is what we have, and hydrogen. In other words, C and H. These are the elements. We've been given here that carbon is percentage composition is 92.3. So if there are only two, so the rest of percentages is hydrogen, and that hydrogen is 100 minus 92.3, giving us 7.7. So we have again the RAM. This is 12. This is 1. So moles. This is 92.3 divided by 12, and this is 7.7 divided by 1. This is 7.7. Working it out here, you get something like, say, 7.7. So you get the simplify. So 7.7 divided by 7.7, you get 1. And 7.7 divided by 7.7, you get 1. So the empirical formula here C ni moja and hydrogen is 1. So from here we can get the empirical mass, which is 12 plus 1, which is 13. And therefore we had molecular mass as 78. So empirical mass times N would give us molecular mass. So 13 times N should be given 78. So N should be 78 divided by 13, giving us 6. And therefore the empirical formula would be CH times 6, which is benzene, C6H6, a major solvent in chemistry. We can still take another example in this regard. We can take still another example on this, and in your own free time you would follow the same procedure. Now the only other thing that we need to connect is that empirical formula, once again times N, should give us molecular formula. Now for the sake of our next lesson, we'll be looking at the concentrations of solutions, dilution of solutions, stoichiometric equations, titrations involving acid-base titrations, redox titrations, and lastly the molar gas volumes. Otherwise, for today's lesson, I think you've enjoyed it, and that we are moving on together. We shall come back and we shall meet. Let me welcome back the Honorable MP to talk to the viewers. Thank you very much.
Thank you very much. I hope our students enjoyed the lesson for today on mole concept. I would like to take this opportunity to thank Mr. Gishui, who is a teacher. Thank you very much. You are recommended by your current students, by your former students, and your colleagues. And indeed, we've seen what you are capable of. We've seen how you've digested chemistry. You've seen how you've broken it into simpler and simpler form. And our next lesson will be next week. And personally, I will be handling that lesson, and we'll make an attempt of at least going to the university level. At least for one lesson, we will handle a lesson involving mathematics at the university level. Then we'll come back again to our students at high school level. Thank you. God bless you all. I hope you enjoyed. And we'll also be giving an opportunity to other teachers. As time passes by, we'll give them opportunities so that at least other teachers can also come and show us what they got. For today, I have some comments here that I want to read, just taking around 1 minute to read comments from Kennedy Ochola. Thank you very much. Mr. Gishui really is doing what he's best at. Another one from Amos Ndegwa. Seems things are really on fire. I know this teacher from before, from Alliance High School. I think this was your one of the people that are successful now in life. Yeah. Luis Farrakhan, this is great. I love the job. Lynette Opondo, good job, Mheshimiwa Babu. Okay, today we had our teacher, Mr. Gishui. Ahmed Mohamed Adi, thank you, teacher. Ken Kipruto, good job, Babu, and good job, Mr. Gishui. Tessie, thank you very much, Babu and Mr. Gishui. Grace Ogola, thank you, Mr. Gishui. This is on YouTube, and then on Facebook. On Facebook, we have Leonard Amimo. I feel like retaking my chemistry again and asking for my school fee back. That's great. Bolton, Seth Bolton, lakini go slow, sir. This is okay, but I've really understood all this. Kijana Dache, rada ya huyo mode yako juu. Iko sawa. Yeah, man. Sister Stesh, exactly. I'm really happy with what the teacher has done. Patrick Ivano, I'm also a fellow teacher. And what the teacher has done, Mr. Gishui, congrats. We love it. Yusuf, thank you very much. Mwalimu. We have Korir. Babu, this is a great job away from politics. This is wonderful. It will help our children. Anthony Thuo, we have indeed learned a lot. Kondir Koli, this is serious development on education. Thank you, Babu. Thank you, Mr. Gishui. Cosmas, Babu, this is great. Moses Maina, Mose, Babu, this is wonderful. Great, thanks a lot. Smolin is saying that Mwalimu Gishui, this is great. I'm sure that my child will pass exams. Sultan, this is Sultan Joe. This is great. Huyu mwalimu ameiva kuiva. Sultan amekupatia heko hapo. Njeri, good work mheshimiwa. Thank you guys. God bless you all. Till we meet again. Now the homework is on the screen. Kindly just follow it and make sure you do your homework. A little advice to our students: make sure in the sciences subjects and also mathematics is a precise science. Ensure that at least you take your 30 minutes on a daily basis to practice. Practice makes perfect. We'll remove you from the slums to the higher echelons of life. Tibim. Santeni.